We're now going to move on to section 1.2, and we're going to look at the learning outcomes associated with periodicity within the periodic table. The first learning outcome states that I can identify groups and periods in the periodic table. So groups are very obvious, they're just the columns and they're identified as group 1, group 2, group 3, 4, 5, 6, 7 and group 0. The periods are the rows. So the first period goes from hydrogen to helium, the second period from lithium through to neon, third period sodium to argon, etc. Now what people have found is that if you plot some property of the element against its atomic number, you get very definite trends. So for example, here we've plotted, it doesn't actually matter whether it's melting point or boiling point or whatever, but some trend against the atomic number. And what we see is that as you go across a period, you tend to increase or sometimes decrease. And then there's a big change when you go from the end of one period to the start of the next. So for example here, this is going across the first period, it's increasing, then you get this big drop. That tells us that this is the end of the period, this is a group 0 element, and this down here is a group 1 element. Then as we go across the next period, which is lithium to neon, we get this general trend with a wee blip up and down of increasing. Then we get another big drop, so that tells us this is group 0, and then this is group 1 again, start of the next period. Again it gradually increases till we reach group 0, then we start another period. So this is another trend. In this case, the trend is decreasing across a period. So we decrease across a period, then a big jump up to the start of the next period. It gradually decreases across the period. Then we reach the end of the period here, have to go down to a new period, and it jumps up again. Goes down across the period, jumps up, goes down across the period. So we get these patterns within the periodic table, and you should be able to use patterns like this to identify where the end of a period is and the start of a new period is. So at the end of the period it's group 0, at the start of the period it's group 1. Now in this section we're going to look at the trends for three specific properties: atomic size, ionisation energies and electronegativities. So let's start with atomic size. And the first learning outcome is that you should know how to use the covalent radius to state the size of an atom. Now the size of an atom is from one side of the atom's outermost occupied energy level to the other side. But it's very hard to pinpoint where electrons are in order to measure that. So instead of measuring the atomic size, we measure the covalent radius. Now here are two atoms involved in a covalent bond, and it's easier with very sophisticated technology to measure the distance from one nucleus to the other. We can actually measure that. And if we half that, we get a measure of the covalent radius, which depends on the size of the atom. So if the covalent radius is small, the atom will be small. If the covalent radius is big, the atom will be big. So we use the covalent radius as an indicator of the relative size of the atom. You should be able to use your data booklet to find the covalent radius of various elements. You'll find it on page 7 of your data booklet, where you've got the covalent radius. So you don't need to learn the trends across a period and down the group. You just need to look it up in the data booklet. So as you go down the group, we see the covalent radius increasing from 37 to 235. You get a similar thing for all the groups. As you go across a period, it changes from 134 down to 71. So it's decreasing across a period. So the trend is, and you look at the data booklet to remind yourself, atomic size decreases across a period, increases down the group. Just notice that in this table it hasn't got group 0 elements. That's because the noble gases don't form covalent bonds, so the covalent radius cannot be measured. The next learning outcome is that you should be able to explain the trend in atomic size across a period and down a group. So here we see the atomic size done as a pictorial picture. So we see it decreasing across a period and increasing down a group. Okay. So why does it decrease across a period? Well, thing to remember that as you go across a period, the number of occupied energy levels does not change. In period 2, all the elements have 2 occupied energy levels. Period 3, 3, etc. So the electron arrangement going from lithium to fluorine. So on lithium it's 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 6, 2, 7. So all with 2 occupied energy levels. Now the size of the atom is going to depend on how far away from the nucleus the outer occupied energy level is. For lithium, the electron in the outer energy level is being pulled in towards the nucleus by the attraction between the electron and the nuclear charge. Lithium only has 3 protons in the nucleus. It's got a charge of 3 plus, and those 3 protons are pulling the outer electrons in towards the nucleus. But fluorine, however, has got 9 protons. It's got a nuclear charge of 9 plus. So the outer electrons, all the electrons in the second energy level, are pulled a lot closer to the nucleus because it's got a higher nuclear attraction, because it's 9 plus as opposed to only 3 plus. So the atomic size decreases across a period because of the increase in the number of protons, hence the increase in the nuclear charge, pulling that set outer energy level closer to the nucleus. Now, what about going down a group? Why does the size of the atom increase? Well, the major reason is that you get an increasing number of occupied energy levels. So fluorine is 27, chlorine is 287, it's got 3 occupied energy levels, bromine's got 4, iodine's got 5. So the greater the number of occupied energy levels, the bigger the atom. A secondary reason is also that the outer electrons in, say, iodine, okay, are shielded from the attraction of the nucleus by all these full inner electron shells. So they shield the outer electrons from the nuclear charge, allowing it to be further away from the nucleus. So let's just go over that again, it's so important. The reason the atomic size decreases across a period is due to the increasing nuclear charge pulling the outer electron shell closer. The reason the atomic size increases down a period is because as you go down a group, every time you go down a group, you add on an extra electron shell, making the atom bigger and bigger. And that's exacerbated by the fact that the outer electrons are shielded from the nucleus by all the inner electrons. Sometimes you're also asked questions about comparing ionic sizes. So for example, it might say compare the sizes of a magnesium ion with a sulfide ion. The way to tackle this question is, well, we know the magnesium atom is bigger than the sulfur atom, both in the same period. This has got a higher nuclear charge, so the atom's smaller. But the question is not about the atoms, it's about the ions. And the way to tackle this is to work out the electron arrangement of the ion. And usually one will have more electron shells than the other. So the magnesium atom has got an electron arrangement of 282. 3 occupied energy levels. Sulfur is 286. Also 3 energy levels. But the magnesium ion is 2 plus, so it's lost 2 electrons, so it becomes 28. Whereas the sulfur is 2 minus, so that gains 2 electrons and becomes 288. So this has only got 2 occupied energy levels, whereas this has got 3 occupied electron energy levels. So because it's got 1, 2, 3, it'll be bigger than magnesium, it's only got 1, 2. So if you ask about ionic size, work out the electron arrangement of the ion, and you usually find one's got more energy levels than the other. Okay, moving on to our second property, ionisation energy. So the first thing we should do is know the meaning of ionisation energy and be able to write the equation for the first and subsequent ionisation energies of elements. So the first ionisation energy is the energy required to move 1 electron from each atom in 1 mole of the element in the gaseous state. So, and this is the way we write it, where E stands for any element. And we mean any element. What they often ask you is to write it for a diatomic element to try and fool you. But it doesn't matter if the element's diatomic, say like hydrogen. The equation would still be H, gas, and it's imperative you put in state symbols. Go to H plus, gas, plus an electron. So don't be tempted to put in H2. So that's the first ionisation energy. You should know where to find ionisation energy values in the data booklet. Okay. So I think it's page 11 of the data booklet. It's got all the ionisation energies for lots of the elements. It gives you the first, second, third, fourth, and electronegativity as well. At the moment we're just going to concentrate on the first ionisation energy. So again we can look at the data booklet to get the trend. So going across a period from lithium to neon, the first ionisation energy increases. Going down the group, say going down group 1, so we've got hydrogen 1312, lithium 520, sodium 496, so it decreases going down a period, down a group. Okay, so again, you don't need to learn the trend, you can just look it up in the data booklet. However, you do have to explain the trend in first ionisation energies going across a period and down a group. Okay, here's this pictograph of the atomic size. So if we remind ourselves what the trend was in the first ionisation energy, as we went across a period, it increased, and as we went down a group, it decreased. So why was that? Well, the ionisation energy you're trying to remove, the first ionisation energy, you're trying to remove an outer electron. Okay. So you're trying to remove that lithium, that electron there. So that's the one in the outer energy level. Fluorine is this one. Okay. Now, the fluorine electron is the same reason as before, because the higher nuclear attraction that fluorine has for that electron, because it's 9 plus, it's harder to remove that electron than this electron, which is only being held by a nuclear charge of 3 plus. So again, the reason is due to the increasing nuclear charge as you go across a period. And the decrease down a group, well, the electron that's being removed in iodine is a lot further away from the nucleus than the fluorine because of the increasing number of electron shells as you go down the group and the shielding effect of the inner electrons. So once again, those two factors are the reason why the ionisation energy decreases as you go down the group. I can explain patterns in successive ionisation energies, so second, third, fourth, and identify the group of an element from these. Well, this is the first, second, third, fourth ionisation energies of sodium, magnesium and aluminium. So the equation for the second ionisation energy, that's the energy required to remove the second electron, not to remove two electrons, but to remove the second electron. So this would be the equation for the second ionisation energy. So for, say, we were looking at sodium, okay, the value for the second, for that, which is the energy required to move the second electron, is 4,562 kilojoules per mole. And just contrast that in the energy required to go from Na gas to Na2 plus gas plus 2 electrons. So that's the equation for removing the first and second electron from a sodium atom. So the energy required to do that would be the energy required to remove the first electron, which is 496, plus the energy required to remove the second electron, which is 4562. So the energy required would be 5,058 kilojoules per mole to remove the first and second electron from a sodium atom. We see that as the more electrons you remove, the higher the ionisation energy gets. So basically, as you remove electrons, it gets harder to remove more electrons, and so the energy required goes up. But if we look carefully, we see that for each element, at some stage we get a very big jump. So for sodium, you get a big jump between the first and second ionisation energy. This goes up to 4562. Whereas magnesium, fairly gentle increase between the first and second, but a big jump to the third. Whereas aluminium, the very big jump happens between the third and fourth ionisation energy. And from that, if we didn't know it was sodium, magnesium and aluminium we were dealing with, we should be able to work out that this is a group 1 element, this is a group 2 element, this is a group 3 element. So let's look at the case of sodium. So the first ionisation energy is the energy to remove the outermost electron. Okay, so it's that one. Okay. But the second, so that was the 496. But the 4562 refers to removing the second electron, which in the case of sodium comes from an electron shell, an energy level which is close to the nucleus. Because this electron is close to the nucleus, it's far harder to remove it than that one. So the big jump to 4562 tells us that we've gone into an inner electron shell. So sodium only actually had one electron in the outer shell. So magnesium's got 2 electrons in its outer shell. So it's the third electron that gets removed from an inner shell. So this tells us that this is in the second group. And aluminium being the third group, it's got 3 outer electrons. So it's a fairly gentle increase as you remove the first 3 electrons, and a huge increase to get the 4th electron out because it's in an inner shell. Okay, and our third and final pattern is electronegativity. So again, we have to know the meaning of electronegativity. So it's a measure of the attraction an element has for bonding electrons. So let's say we've got two atoms bonded together and they both have the same electronegativity. Let's just say it's 2.0. They both have the same attraction for the bonding electrons. So the bonding electrons will be in the middle of the bond. They don't prefer one element over the other. Whereas if we were two different elements, X has got electronegativity of 2.0, let's say Z was 2.5. 2.5 has a higher electronegativity, a higher attraction for bonding electrons, which means the electrons will hang around closer to Z than X, making this bond slightly polar. Because the electrons are near the Z will be slightly negatively charged and the X will be slightly positively charged. If there's a very big difference in the electronegativities, say that was 2.0 and this was 4.5, in fact W would just grab both electrons and have a negative charge and become an ion, and X would be positively charged. So electronegativity, measure of the attraction the elements have for the bonding electrons, and as you are aware it has quite a lot of effect about polar molecules in due course. Right, you should be able to know how to use the data booklet to find the electronegativity values for the elements. Well, here they are here on the same page as the ionisation energies. Trend tends to be the same as the ionisation energy, increases across a period, decreases down a group. You'll notice there's no value for noble gases because they don't form bonds, so don't have an attraction for bonding electrons. So we should be able to explain the trend in electronegativity values across a period and down a group. So the electronegativity increases across a period, and like the ionisation energy, decreases down a group. They increase across a period, as always, because of the increase in the nuclear charge. So the fluorine has a higher nuclear charge, 9+, than the lithium, and so it's going to attract bonding electrons more strongly than lithium. And the reason it decreases down the group is because the bonding electrons go into the outer electron shell, which for iodine is far further away from the nucleus than for fluorine, because it's got more outer electron shells, and the electrons in those outer electron shells are shielded from the nucleus by the inner electrons. So it's basically the same explanation, kind of works for atomic size, ionisation energies and electronegativities. Okay, so that's all the learning outcomes from that section. Make sure you'll be able to explain those trends in atomic size, ionisation energies and electronegativities.